In this video, we're going to very quickly look at the Newton-Raphson method and how it is used to find a better approximation for a root of an equation. Okay, this graph shows a curve with a root at a point R. So that's where the actual root is. So the root of something, remember, is where it crosses the x-axis. So that's where the actual root is. And you may have x0, which is your first guess of an approximation to the root. And what Newton-Raphson does is it allows you to find a better approximation from the root. Okay, you should have seen in the last video, which was on location of roots, how you can find where a root is, i.e. between 2 points, maybe between x equals 1 and x equals 2. So for example, if you knew your root lay between x equals 1 and x equals 2, a good starting point for your first guess would be 1.5. Okay, and then from that, then you can use Newton-Raphson method, and maybe it gives you 1.7 is a better approximation. And then maybe your next one is 1.72, and next one maybe is 1.723, okay, and so on and so on. So it gives you a better approximation to your root. We're going to see how that works in practice. On the screen, you can see the Peripheral Newton-Raphson method, and that goes back to the diagram we had up above. The gradient would be f of x0 over x0 minus x1, and then if you substitute your m is equal to f dash of x. So here, remember, f dash of x means the derivative of f of x. Then that gives you f dash of x is equal to f of x0 over x0 minus x1. And then just multiply across, or switch this f dash x with the x0 minus x1. You can see you get this next line. And then just bringing the x1 to one side, you see x1, which is your better approximation, is equal to x0 minus f of x0 over f dash of x0. Okay, thankfully the proof is not needed. You don't actually need the proof, but what you do need is to be able to understand this formula. So the formula is the following. So this formula here, i.e. if x is a good approximation of the root of f of x equals 0, then x1 equals x0 minus f of x0 over f dash of x0, and that, very importantly, is a better approximation. Now, another way we can write that, which is very useful, is the following one. So this is an iterative formula. So that means to get your next approximation, it's xr, which is your current approximation, minus f of xr, your current approximation, over f dash of xr. And that really is what's known as the Newton-Raphson formula. So we're going to work through an example here and see exactly, two examples, sorry, and see exactly how we're going to do this, and especially using this version and a quick way we can do it, and a quick way that we can set it out. Okay, our first example says solve x cubed equals 4x squared minus 4 using the Newton-Raphson method. Correct the two decimal places in order to find the root near 1. So the root near 1 would lead me to think that that would be a good thing to have for my first approximation. So my first approximation, x0, is 1. Now we're going to have to rearrange this thing a little bit so that it would be equal to 0. So I'm going to do that by just bringing everything over to one side. So, and then I'll say then f of x then is equal to, it would be x cubed minus 4x squared, and then plus 4. And while I'm here, I'm going to work out what my f dash of x would be, and it would be 3x squared minus 8x, and then we can then put that into our formula. Just as this is new to us, we're going to write down our iteration formula, and this would be good practice in the exam as well. X of r plus 1, so that's to get your new approximation. It's equal to xr, which is your current approximation, minus f of xr over f dash of xr. So our first approximation was x0, and x0 was equal to 1, and then we can just write down what we get for the next few. And I think I only need to go to the first four, I suppose, the x0 all the way to x3. Right, we're going to look now how we actually do this on the calculator. So how do we actually do this bit here on the calculator? So on your calculator, our first approximation, remember, our first approximation is the x0, which is equal to 1. So on your calculator, what you want to do is press 1, because that was your x0, and then press the equal sign. Now what that does, that means 1 is now the current answer in your calculator, and we're going to use our answer button to do this then. So then what you want to do, so if we're looking at the back of the bit that I have highlighted in green, it was the current approximation, which was R1, which is our answer button, remember, minus, and then you're using your fraction button in your calculator. And the top line of that fraction was the f of x, so which was x cubed minus 4x squared, sorry, where I'm getting this from, x cubed minus 4x squared plus 4. So instead of putting in x, anywhere you see x, you're going to put your answer button. So we're going to write that as, it's whatever your answer is, cubed minus 4 times your answer button squared, and then plus 4. And then your bottom line was 3 times your answer button squared minus 8 times your answer button. Okay, then if you press equals, you will get your next approximation, and then press equals again, you will get your next approximation, press equals again, you will keep getting all the next approximations. So I'm just going to write that in, so we'll just say it then, press equals, to get the next, to get successive approximations. So if you put that into your calculator, so it was, you press 1, go through that again. First of all, your first approximation is 1, so you push 1 and then press equals. That's now what's stored in your calculator as the answer button. And then you want to do this thing, so it's that thing, so it's answer minus, and then your f of x, remember, was x cubed minus 4x squared plus 4 over 3x squared minus 8x. So you do your answer button minus answer minus your fraction button, and then you're doing the top line of your fraction is the answer cubed minus 4 times the answer squared plus 4. Your bottom line is 3 times your answer squared minus 8 times your answer, and press equals to get your successive approximations. So when I do that, so literally I've done the hard bit once I've got to there, and then just press equals, and the next approximation I get is 1.2. The next one I get is 1.939. The next one I get is 1.1939 again. So you can see already it's pretty much derived at, it's going to certain things. So obviously I haven't shown all the decimal places, but I've got enough because I just need to go to my 2 decimal places. If you're unsure, if you don't believe that, folks, just keep pressing equals and you'll see it will, to 2 decimal places, it is going to go to my root then. It's going to be, the 2 decimal places is 1.19 brackets to 2 dp. Okay, this example says taking x equals 2.3 as the first approximation to the positive root of 3 sine x equals x using Newton-Raphson method for 2 iterations to find a better approximation. So it's only telling us to use Newton-Raphson twice, so we don't have to go to a number, we don't have to keep going indefinitely or anything, just 2 times. And also there's a very important thing that happens in this question because of the 3 sine x. Okay. Right, first of all, we have got 3 sine x involved. Remember, if we are differentiating or integrating, if you're using calculus at all on trig, your calculator must be in radians mode. So first thing you have, and just in general, folks, if you're doing Newton-Raphson method, remember there's part of it involves differentiation. So just put your calculator in radians mode and then you'll be fine. So just say put calculator in radians mode. Okay, because sine of 2.3, for example, will be different depending if your calculator's in radians mode or degrees mode. So that's our first thing. We're going to write down our f of x. You have to let your f of x be something. So bring everything to one side in this, so it's equal to 0. So, and then you can put that equal to your f of x. So it's going to be 3 sine x minus x. And then we're going to differentiate that to get your f dash. And that's going to get you 3 cos x minus 1. We'll write down our iteration formula. X, r plus 1. So this is to get your next term. you do your current term minus f of xr over f dash of xr. And remember, your first term, x0, was equal to 2.3. So I'm going to show all the working out. I'm not going to do the calculator method this time necessarily. I'm going to just show the steps here, just to show where it's coming from. You can use a method I've used in the previous one if you want. That will be fine. But I'm just going to show exactly where it comes from this time. So x1 would be equal to 2.3 minus, and then f of 2.3, which means 3 times sine of 2.3 minus 2.3 over 3 times cos of 2.3 minus 1. And when I worked that out, I got 2.27903 ... That went on for a bit. And then my x2, and this is as far as I need to go, is going to be 2.27903 ... Then minus 3 times, I'm going to run out of space here, sine of 2.27903, I'll put that in a bracket, minus the 2.27903, just about squeezed on there, and then divided by, and then the bottom line is going to be the 3 cos of the 2.27903 minus 1. And when you do that, you will get 2.27886. And did we have to go to a certain number of decimal places? I don't think it told me to, but I'm just going to go to 2 decimal places. That's going to be 2.28 to 2 decimal places. Okay, and that is it done. Right, our very last thing in the notes here, I'll leave that on the screen so you can see it for a bit. It says, if the question involves trig, remember to work in radians. If the approximations don't converge, then the initial value must be incorrect. So if you've done something and you're hitting equals on your calculator to see, just using the previous method I'd done, and it's not converging, so it's not going to the same values appearing on your calculator, either your first approximation is incorrect, or else you've maybe made a mistake somewhere around here, for example. It could have happened as well. Okay, so watch out for questions requiring an approximation to the tangent, not the function. I use differentiation. Right, that is that done. The next video we're going to be looking at what's called the Simpson's rule, the trapezium rule, to find areas under curves. So that will be the last of our numerical methods videos.